All right, we're going to take a quick look in topic 5.5 and 5.6. So we are looking at collision theory, which you watched a short video on, and then what are called reaction profiles. So we're going to take a look at the reaction profiles, and which are essentially graphs, and identify some different parts of it and how we read these graphs. So a reaction profile is essentially, it shows the reaction in terms of its potential energy on the y-axis, or how much energy is stored in the chemicals, and then time. Sometimes it says reaction progress, that kind of thing. So we're not really marking specific times. We don't really have a scale on this, but typically there is a scale of some sort on the y-axis. So we're going to identify first all of these pieces that are labeled at the top. These are their definitions, and then we're going to label them on our graph so we can see how the two relate together. So first is our energy of the reactants, our initial energy. And this is the amount of energy indicated at the beginning of the reaction graph that shows the energy contained in the reactants of the reaction. So that says reaction a whole bunch of times, but essentially this is our energy of our reactants, 45 kilojoules. And these are our reactants in our chemicals. So it shows that they are about to collide. So each of those would have their own stored energy, and it adds up to 45 kilojoules of energy. All right. So this is A from up above, so we can label those pieces. Letter B is the energy of the products, or our final energy. This is the amount of energy indicated at the end of the reaction graph that shows the energy contained in the products of the reaction. So over here is B, our energy of our products. We can see they are not the same chemicals as our reactants. So they have 10 kilojoules of energy there. All right, so that's A and B, our reactants and our products. Part C is the energy of the reaction, the change in energy. So we've got a final and an initial energy. To find a change, it is the difference between the reactant and product energy on the graph. Products minus reactants, final minus initial. If the reaction energy is negative, it's exothermic, and positive, it's endothermic. So essentially, it is the change in energy. So where our products are and where our reactants are, it's this difference, okay? So we do products, which is 10 kilojoules, minus our reactants, 45 kilojoules, and we would get negative 35 kilojoules. Okay, it being negative tells us it is exothermic in this case. Okay, so this is an exothermic reaction based on that. Okay, we always do final minus initial. So this is our change in energy. How much energy was lost by the reaction in this case? So 35 kilojoules was lost. Or if our products end up higher than our reactants, then we gain energy, and it would be endothermic. Okay, so these terms might be hopefully are familiar to you. Were learned in honors chem, but exothermic generally means a release of energy from our reaction or system. So if we have our reaction, our system happening, then it is giving off energy, which is why it is a negative energy. If it takes in energy, then it's going to be positive, and it's endothermic. Okay, so we can imagine them that way. All right, part D on our graph, the activation energy. Activation energy is the energy required for a chemical reaction to occur. On a graph, it is the energy from the reactants to the top of the energy graph. The difference is the activation energy. So again, we're doing a change in energy, and it is from the reactants, where they start, to the top. So a lot of times this is labeled as E for energy, and then a little A for activation. So energy of activation, or activation energy. So it's the energy that these chemicals need when they collide to have a successful reaction. All right. So if they don't have that, it's like trying to run uphill without enough energy. You're just going to stay on that side of the hill, right? If you can't make it up, then you're just going to fall back down. But if you have enough energy, then you can make it over the hill and make your products. Right? So that's our activation energy. In this case, Again, we always do the final minus the starting. Our final would be 103 minus our starting of 45, all in kilojoules. So, I don't know that off the top of my head. 103 minus 45 would give us 58 kilojoules for activation energy. Okay, it's always the difference there. This is a common when I see students label the peak it by itself, and they'd say the activation energy is 103, but it is that difference that is key there. All right, and our last part, one more color, is looking at activated complex. The activated complex is also called the transition state, and it is a complex chemical that is made in the instant, that quick time, that the chemicals successfully collide. It will be at the very top of the energy graph. This here is part E, that's our activated complex or our transition state. So we can see that the collision is happening between the two atoms that are shaded in, and those are colliding here, and then they stay together and the other atom that's not shaded separates. So when they're all kind of stuck for that split second where they hit, that's the activated complex. It has enough energy and it is colliding. All right. I didn't label a couple of these. So our activation energy, that was part D, and our energy of reaction was part C. So there are all our labels. So a lot of times we might be asked questions about a graph like this. So we'll just fill these in based on what we saw there. So what is the energy of the reactants? We found that already to be 45 kilojoules. And the energy of the products was 10 kilojoules. The activation energy was that difference, so 58 kilojoules. The activation energy also is always positive because we have to gain that energy to make our products. The energy change for the reaction, that change there was negative 35 kilojoules. Since it's negative, that tells us it's exothermic. And it says draw an unsuccessful collision between the reactants. So a successful collision is what we can see here, where these two atoms, they want to collide and form our product. So let's just look at what the successful reaction would look like, and then we'll make the unsuccessful. So we can see both. I think that's a good way to do it. So successful would be our open circle and our shaded circle, and that's colliding with that open circle, right? And the collision is, oops, I should have done an arrow. Those two parts are colliding with each other, and then it is making the two shaded circles are together, and then we have our open circle. Okay, so that's our successful collision. Excuse my terrible arrow there. So our unsuccessful would be if these two atoms that want to come together don't collide. So say I turned and I flipped around my molecule here, and the two that collide are those two, open circle and the closed one. Well, that does not create a product. Okay, no product. They would bounce off of each other, or if anything, we create the exact same chemical, right? This one switches over here and we get the same chemicals. So that would be an unsuccessful collision. So that's how we read these graphs. These again are reaction profiles. On the following pages, you've got some practice on that. The one part that seems to always throw people off is just writing the chemical reaction. So this got shifted a little bit. That should be those two chemicals on top. I had to do some little edits here. So those chemicals. So it would be your reactants here, your arrow, and then your products there. So it's basic chemical reaction. So as an example, 2A plus B makes A2B. That would be our chemical reaction. All right. From there, you can read your graph, fill in all of your information. You've got some different ones there, and then some multiple choice type questions to answer about collisions and collision theory and graphs. All right, guys, thanks.